we're going to talk again a little bit about chemistry. This is section 4.2 in our Abeka chemistry book, Precision and Design. And this is page 52. So we're going to talk about classifications of chemical reactions. Because of the nature of the video, and we had to keep it fairly short and fairly simple where I am right now with just a blackboard. We're going to be very simple and just give you some things here. Otherwise, we'd have some things to show you, some things to see in hand and in class, but we won't have that today. But every reaction that we're going to deal with at this point is falls into one of four categories. And those categories are what we have listed here: a combination, a decomposition, a single displacement, and again, I apologize for the downward, but the way I write on the board with no lines, my writing just tends to go down. Anyway, a single displacement and a double displacement. Sometimes you're going to run across things in your book, or maybe another book, or somebody say something about a synthesis reaction. Now, when we talk about a synthesis reaction, that's a combination reaction. That's where we're putting things together, we're making something, so we're synthesizing something. So sometimes you'll see that here, and I'll go ahead and write that synthesis. It's also called a synthesis combination, a synthesis reaction. And then you may see something called, when we get down to the single displacement, sometimes it's called a substitution reaction. It could also be called a single replacement or a displacement reaction. But I think for the most part in this book, you'll see them refer to it as a single displacement reaction. So let's talk about these first and what they are. Reaction where two or more substances come together in order to form one substance is called a combination reaction. So you can see right here, let's say we have A plus B, and we have A plus B. And whatever the case, or however the reaction occurs, there's different ways for that to happen. But this reaction does occur, and two different substances come together to form one substance. Two reactants forming one product is called a combination. And our example of that is going to be a carbon, solid carbon, plus a gaseous O2. Remember the O2, it's a diatomic element. We talked about that. And it's going to produce a gaseous CO2. So if you put a solid carbon and a gaseous oxygen together, it'll produce carbon dioxide. So what we have is two different reactants coming together to form one product. And so it's a two, or more, coming together to form that one product. And there are some more complicated synthesis reactions, but right now we're starting with the simple, and we'll build on those as we go throughout the book. And so that is the combination or synthesis reaction. We're going to look at also in our book, and we won't go through all the examples that they give us, but there's also what's called a decomposition reaction. And this reaction can also be known as the breakdown reaction. So it's breaking things apart. Now, real quick, with a breakdown or a decomposition reaction, those usually don't happen just by themselves. Now, our whole universe by itself has what we call an entropy, and it is reverting to chaos. God made it in such a perfect way, but He did tell us in the Bible that in essence the world universe is wearing down, wearing out, or going back to a chaotic state. And so things do naturally wear down. But this type of process that we're talking about, this decomposition or this breakdown reaction, typically needs one of two things. You say, well, what do you mean it needs one of two things? It needs either an electric current or it needs heat to help it happen. Remember we talked the other day about delta being heat? So it needs one of these two things, either an electric current or heat to help it happen. Not always is that the case, but most of the time it is. So what we have with a decomposition is we have something that's here together. We have well, in this case a reactant, and something's going to be done to this reactant. That's why we say something is done to the reactant, an electric current or heat. Sometimes it could be light. Some things are so reactant to light. Have you ever been to the store with your mom or seen in your cabinet at home, maybe in the bathroom, a kind of a bottle about this size, maybe the size of a Coke bottle, but much fatter, and it's all brown? And what do we call that? That whole brown, not the stuff on the inside, it's clear, but that brown bottle is hydrogen peroxide. You know why they make it in that brown bottle? Well, it's because that's very reactant to light. And so if light gets in there, it starts to react, and they and we don't want that to happen. So it's not just an electric current, not just heat that can make things react. But in this case, we're going to need either, we're talking about today, electric current or heat. So we have one reactant, something happens to this reactant, breaks it down into two different products. So from one reactant to two different products. And so that's what happens here. AB yields A plus B. AB yields A plus B. Two different products. Our example here is we have 2 aluminum oxide is going to yield with an electric current 4 aluminum with 3 O2, 3 O2 gaseous. So again, we have one, I know there's 2 of them, but there's one molecule that's breaking down to 2 separate atoms. And by the way, I want to say this real quick, well, we'll get to it in just a second down here. We'll explain some things, especially with the double displacement, it'll make sense. We'll hold off till then. So we talked about our combination, 2 different to 1. We talked about the decomposition, 1 to 2. And now we're going to talk about a single displacement. So what we have in this case, we have A plus BC is going to yield B plus AC. So we have A plus B and C, and something happens with that reaction, and then it's going to yield B plus AC. And so what happens is, you can see by this basic equation, is that A is going to move in and kick B out, and B is going to have to come back over here where A is, which is exactly what we have on this side of the reactant. A moved in to join with C, kicked B out, and B came over by itself. Let's see real quick an example equation. Well, we have 2 sodium, solid, plus 2 H2O, a liquid, is going to yield a hydrogen gas, H2, remember diatomic element, plus 2 sodium hydroxide. Now real quick, if you want to, by the way, we're going to come back to 53 in just a second, page 53, but look at page 54, the top left-hand picture on your paper. You're going to see a little jar with sparks shooting everywhere. That is sodium reacting with water. Very, very dangerous because sodium is highly reactive when it comes to water. You could rub pure sodium on your fingers, and just the water that's in the air can burn your fingers and cause some problems there. So we don't play with pure sodium, and especially around water. It could be dangerous, but you can see how reactive that it is. But when it does react, it produces a hydrogen gas and sodium hydroxide. And so we again, we'll maybe talk in the future a little more about these reactions. But then there's one last reaction. That is the double displacement. So I've got to get a lot of markers here in order to do that. So what happens, you can see, is we're going to have an AB plus CD. And so whenever they do switch, the AB plus CD, they're going to switch just like this, and it's going to be an AD plus ACB. Now, I'm going to point this out. It may be obvious or seem obvious that when we have A, B, and C, D, that the A is just coming over here and C is coming back over here. It may seem obvious, but what we can't do, I couldn't write AD plus BC. It has to be, I can't do that. That's a no. Can't do that. Has to be CB. And the reason that is because of the charges on the ionic compounds. We always say the charges plus and then minus, plus and then minus. So if A and C are the pluses, A and C still have to be the first that's mentioned. And that's just the way we work our molecular formulas, especially our ionic formulas. Look at our example real quick. Na2SO4, that is sodium sulfate. It's an aqueous solution, and BaCl, barium chloride. Now, real quick, notice that it's an aqueous solution too. Typically, at least the ones we're going to talk about here, aqueous solutions for double displacements. That's just the way it works. Now, it doesn't always produce aqueous products. As a matter of fact, typically we want to see a solid in there. There's going to be a particulate that comes out of those mixing. But when we have the sodium sulfate and barium chloride, it's going to produce sodium chloride and a barium sulfate. Interesting thing about this is still an aqueous solution. It means it's water-based. It's mixed with in the water there. Sodium chloride. Do you know what a sodium chloride is? NaCl. What we would say sodium chloride is? That's a salt. And so we'll talk a little more about salts later on in our book. But probably, and I know these are all of our interesting formulas that we've talked about, maybe some interesting reactions that we may be able to see some this year, but probably the easiest way to classify some things or some equations, especially what you're going to see in your homework, is just by using these, the ones that we have written in green here, the A's and the B's, and down later C's and D's. But just remember, if we're putting two together to make one, it's a combination. If we have one, they're breaking apart, decomposition. If we have one and two, and then over here, one of those are switching spots, single displacement because it's one displacing. Down here, two and two, where the two front ones are switching spots, well, it's going to be a double displacement. All right, and that's pretty much it for classifying these types of reactions, and you can see your homework there. If you have any questions, let us know. I did want to go back and show you something real quick on page 53. If you want to look at that leavening agent, it's kind of interesting. A substance that causes, our book tells us, that causes dough to rise is known as a leavening agent. A lot of familiar leavening agents. One of them, probably the most familiar, is yeast. Maybe we're used to seeing, but what happens with a yeast, a type of fungus, it ferments, it produces carbon dioxide and an alcohol, and so that carbon dioxide will want to escape, and it'll bubble up, and it'll make whatever that yeast is rise, whatever that yeast is in rise. But probably a more familiar leavening agent that we've seen is probably it's called baking soda, and we've probably seen that in Mom's kitchen, baking soda. A pretty interesting thing about baking soda, or what we call sodium bicarbonate. And you may have heard maybe maybe your grandparents say sodium bicarbonate. Maybe they talked about taking some sodium bicarbonate if their stomach hurt. We don't necessarily take that anymore. We have different medications for that, which are sodium bicarbonate based. But nowadays, or back then, they just called it sodium bicarbonate. So, and you can see in your book that there is sodium bicarbonate when it's heated, as during baking soda thermally decomposes to produce a gaseous CO2. So this is a decomposition reaction there. So, and you can see the formula in our book: 2NaHCO3 aqueous with heat added yields an Na2CO3 plus CO2 and plus H2O plus a gaseous water vapor. There was another leavening agent that's very, very similar to baking soda, that you may have seen in mom's cupboard, mom's kitchen. That's baking powder. And so what's the difference? Baking powder is a mixture of baking soda, and so it's a solid substance that forms an acidic solution in water, our book tells us. But with that, there is something maybe like a cornstarch, something to keep that baking soda very, very dry. And so sodium bicarbonate readily acts with the acids to form CO2 gas, our book tells us, when it's heated, and as long as the baking powder is kept dry, no reaction. And that's the way the baking powder is meant to work. And so both of those really boil down to the fact that why they have them stuck where they are in the book. Both of those are decomposition reactions. So that's maybe something you can see at home. And if you've never done this before, you can take maybe a little glass, and if you have vinegar or even water, but vinegar would work well. But you put that in there, and you put some baking soda or even baking powder in there as well, and mix it, and you'll see some bubbles form. Those are carbon dioxide bubbles. That's a decomposition reaction that's happening. It's one thing breaking down into another. So hopefully that'll make some sense to you, these classification of chemical reactions. And we'll get on into some other things with our chemistry upcoming, and quantitative relationships from balanced equations. And once you get a good grasp on these things now, so it's not so difficult later on in the book. But if you have any questions about chemical reactions or classifications, let us know. I'll be glad to help.